Okay, so today we're going to look at an example of a trig substitution integral problem. In particular, the example that I want to do is to evaluate the antiderivative of 1 over 4 minus x squared quantity to the 3/2. Now, as usual, I just started this by saying we're going to do a trig substitution, but it's always good to keep in mind that when you get an integral on the test or in the wild or in the real world, you don't know where it came from. So you have to be able to figure out yourself that that's the thing to do. So in my opinion, it's always a good idea to start off by looking at this and asking yourself, are there any simpler techniques that I could do, or is there anything else I could do? So usually the first kind of question I ask is, can I do any algebra? Any obvious algebra? Nah, I don't really think so. We could factor the bottom here, but I don't really know if that would get us anywhere. The other thing that might stand out is there is a very obvious composition of functions in the denominator. I have blah, 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 blah to the 3/2. So if there's anything that might work, which is simple, it could be a u substitution where you just call u 4 minus x squared. You could try if you want, but it doesn't seem likely to work just because if you were to call u 4 minus x squared, your du would be 2x, and then it's a little hard to work with that. But give it a shot if you want. Would we integrate by parts? It doesn't feel like an integration by parts problem. That's a little vague. The only other thing that you might consider is something like partial fractions, but the fact that this exponent here is a fraction, I don't think partial fractions is a very good idea. Okay, so maybe we've ruled out any other reasonable technique. What's the point of a trig substitution? The point of a trig substitution is that I look at the thing in the denominator here. It looks really scary. I think, oh my god, I don't know what to do. Maybe I can use a trig identity to my advantage to simplify this. That's the philosophy behind doing a trig substitution. Now, what do I mean by that? So I just mentioned that we want to use a trig identity to help us. Well, how many trig identities do I know? I pretty much know one. Here's the trig identity I know. It's cosine squared theta plus sine squared theta equals 1. So I think about this and I ask myself, is there any way I could use this to my advantage to simplify an expression like this? Well, this doesn't look so much like this unless I move one of these terms over to the other side. The reason why I'm doing this is because I look at this expression and I see a constant minus something squared. So if I do a little simplification here, for example, by moving the sine squared theta to the other side, I get cosine squared theta equals 1 minus sine squared theta. And now I'm starting to see some similarities with the integral that we have. They're vague similarities, but what I mean by that is over here I have a constant minus something squared, a constant minus something squared. Now, one issue is that while the constant over here is 1, the constant over here is 4. 4 is not 1. Okay, well, what could I do? I could just force this to be a 4 by multiplying both sides here by, say, 4. Now I have 4 minus something squared. Okay, well, what does this have to do anything with this integral? Right now, nothing. But what I think now is that, gee, I really wish x squared, I really wish this thing looked like 4 sine squared theta. Because if it did, I could use this trig identity to my advantage and maybe simplify that expression over there. So let me think that. I really wish x squared, this chunk right here, looked like this. Now what would this tell me about x if I took the square root of both sides? It would tell me that I really want x to look like 2 sine theta. If only. Well, how do we make that happen? This is what a variable substitution is. We just declare it to happen. So the thing about trig substitutions is it's presented as this new complicated fancy technique, but it's really not. A trig substitution is just a variable substitution. You already know how to do these things. And when you first learn something like a u sub, it's kind of presented like, oh, you call u this thing because of this, but the truth is you can call anything else you want all the time. As long as you change everything accordingly, you can do whatever you want. So in particular, if I really wish x looked like 2 sine theta, I just speak it into existence. I say, let x equal 2 sine theta. There's the trig substitution. And again, from here on out, it's really not any different than doing a regular u substitution. We just have to figure out how to rewrite everything in the integral to be in terms of our new variable. So the details are a little different, but the general idea of a trig substitution is nothing new. You already know how to do it. Okay, so we've declared x to be 2 sine theta. As always, with variable substitution, the other thing that we have to figure out how to rewrite is dx. You have to always change the differentials. Well, again, just like in a regular u substitution, how do you do that? You just differentiate both sides. Hit both sides with d, and this says that dx is going to be, the derivative of sine is cosine, so I'll get something like 2 cosine theta d theta. And then with this information and this information, we can take this integral here and completely transform it to be in terms of our new variable theta. So, taking the original integral here and transforming it into theta, what do we get? We'll get the integral of 1 over quantity 4 minus x squared. By construction, x squared is 4 sine squared theta. Quantity to the 3/2. Oh my god. And then dx turns into 2 cosine theta d theta. And then you look at that and you say, Joe, that doesn't look any better than what we started with. It probably looks even worse. And I agree, but the idea here is now we can do a whole lot of algebra to simplify this a lot. The whole point of doing this was to first use this trig identity. So the first thing we're going to do is, well, 4 minus 4 sine squared theta, I can rewrite that as 4 cosine squared. So let me rewrite this a little bit. The 2 cosine theta, I'll just put in the numerator of the fraction. And then downstairs, I've got 4 minus 4 sine squared theta, which is exactly 4 cosine squared theta. Okay. Looks a little better. And we can keep going because we just have powers of cosine here. So what you want to do is you just want to simplify it as much as you can. So the next thing that I would probably do is I have some annoying constants flying around that don't really matter, so I'm just going to pull them through the integral. So I get a 2 over, when I pull the 4 through these parentheses, it picks up a power of 3/2, so in the denominator I'll get 4 to the 3/2. And then I have the integral of cosine theta over cosine squared quantity to the 3/2. And then the idea is cosine squared to the 3/2. This is the same thing as cosine squared, cosine to the 2 times 3/2. 2 times 3/2 is 3, because the 2's cancel out. So the denominator, when you simplify it here, is just cosine cubed. So continuing from down there, we would get, let's see, so the other thing we could do here with the constants is 4 to the 3/2 is like 4 to the 1/2 quantity cubed. 4 to the 1/2 is the square root of 4, so this is like 2 cubed. So we got a 2 over 2 cubed, cosine theta over cosine cubed. And then cosine over cosine cubed is 1 over cosine squared. 2 over 2 cubed is 1 over 2 squared, so this will be a 1 over 4 integral of 1 over cosine squared. Ooh, and that looks a lot better, maybe not, than the thing that we started with. But the idea behind a trig sub is exactly that you start with something that you don't know how to integrate, use a trig identity to your advantage to simplify things algebraically, and then cross your fingers and hope you get something that you do actually know how to integrate. Okay, so we have to figure out how to anti-differentiate 1 over cosine squared. And again, if you can see what to do, great. If you can't, then probably what you should be thinking is like, well, I learned how to integrate powers of sines and cosines, but the cosine's in the denominator, so that makes it a little awkward. So the rules that I have for that don't really hold. The key here is to recognize that what is 1 over cosine squared? That's exactly secant squared. 1 over cosine is secant, right? So the integrand, when we rewrite it in terms of secant, is secant squared. And then the idea is if you know your trig derivatives pretty well, it should stand out as something that we can easily do, because what's the derivative of tangent? It's secant squared. So I look at this, I remember that the derivative of tangent is secant squared, which tells me that, the antiderivative here is just tangent. Okay. So I've got a 1/4 tangent theta, add a plus c for good measure, and we've succeeded in doing the integration. Now the question is, are we done? No, we're not. I've erased the original integral, but the original integral that we started with was in terms of x. So as always, just like when you do a regular substitution, your final answer needs to be an x. So the next thing that we just have to figure out how to do is we want to rewrite tangent of theta in terms of x. How do we do that? The first thing I want to do is show you something that is not wrong, but it's not the best way to do it. So here's maybe your first inclination if you get something like tangent theta and you want to rewrite it in terms of x. you say, okay, well, let me go back to my original substitution, which was here. So again, I'll do this in a thought bubble. It's not what you want to do, but I just want to show you what it is, because I imagine it's very tempting to want to do. So not the best way is to say, well, if x is 2 sine theta, let me solve for theta here. How would I do that? I would divide by 2, so I would get sine of theta is x over 2, and then apply arc sine to both sides, and you'll get theta is arc sine of x over 2. So if theta is arc sine of x over 2, tangent of theta, well, this is just tangent of arc sine of x over 2. Done, right? And again, you're not incorrect. The problem is, like, well, first of all, this is really ugly looking, and math should be fun and pleasing and aesthetic, and I don't think this counts. But that's not the real issue. There is no real issue, but you know, if you walked up to a person on the street and you said, hey, you want to see what my favorite function is? And they said, yeah, sure. And you said tangent of arc sine of x over 2. What does that mean? If I asked you to graph this, would you be able to? Maybe. But it'd be kind of hard, and it'd be a little weird just because tangent of arc, it's extremely weird to deal with. And it turns out that instead of just doing this, we can actually rewrite tangent using only x's. We can get an expression that doesn't involve any trig or inverse trig functions at all. And if you can do that in general, that's a preferable way to go about rewriting tangent. Okay, anyway, enough talking. What's the better way of doing this? I'm still going to use the original substitution. This is the key, but I'm going to use it in a little different way. So to continue my solution, I would say, all right, well, next, recall that the original substitution, which I just erased, is 2 sine of theta for x. What I'm going to do is I'm going to take this information and interpret this in a right triangle. So we get to go back to high school geometry or whatever and think about what sine of theta tells us about a right triangle. In particular, if I divide by 2, this data here says that sine of theta is x over 2. Okay, what's the point? The point is that if I draw a right triangle, almost a right triangle, with angle theta, what does sine of the angle represent? SOHCAHTOA, sine is the opposite over the hypotenuse. Sine is the opposite over the hypotenuse. Opposite over the hypotenuse. Opposite over the hypotenuse. If sine of theta is x over 2, I can interpret that in my picture up here as saying that this edge of the triangle is x, and this edge is 2. What's the point there? I can use the Pythagorean theorem to solve for this unknown side. So the unknown side, by Pythagorean theorem, if I call this star, says this thing squared plus x squared has to be 2 squared. Solve for the unknown thing, and that tells us that this unknown side here is the square root of 4 minus x squared. By the way, this shouldn't be surprising because if you think about the original integral that we started with, we had an expression exactly like this. Usually when you're doing a trig sub problem, that's an indication that you are doing the right thing. In any case, the point is that here's the data of a right triangle with angle theta, and we're trying to figure out what tangent of theta is. But then I can just read this off the picture because tangent of theta is the opposite over the adjacent, so katoa. Well, opposite over the adjacent, this tells me that tangent of theta is x over the square root of 4 minus x squared. And that looks a whole lot nicer than something like tangent of arc sine of x over 2. This is much, much easier to understand. And then we're done, pretty much. Plug back in here, and that's the integral. So to summarize, the integral that we started with, which I've long erased, but it was 1 over quantity 4 minus x squared to the 3/2 dx. We figured out is 1/4 times tangent theta, so that's 1/4 times this, and we're done. There we go. That's a trig substitution.